All right, how's it going, everybody? We are here on Thursday, March 4th, and today we're going to talk about section 7.6, product some product formulas. And by the way, if you're here watching this live, I'm going a little bit out of order here with my schedule just because of a meeting that I have today this afternoon. So, I'm kind of doing if you're watching live, I'm breaking my schedule a little bit here, but for those of you, which is a majority of you watching the video afterwards, no difference right here. So today we're getting our kind of last day of a bunch of our formulas associated with our trig relationships, right? We talked about identities in 7.3. Then we've been building kind of families of identities in 7.4, 7.5, 7.6. We got our sum and difference formulas. We got our half and double angle formulas. Today we're getting formulas that are going to convert products of trig functions into sums of trig functions and the other direction, sums of trig functions into products of trig functions. I laugh that I think that mathematicians in general are pretty funny about naming things because either the names are ridiculous and meaningless or the names are like the most explicit thing. It's like it's a toaster, it makes toast. That's the style of this right here. It's the product to sum formula. It converts products into sums. Like it's pretty straightforward. If you've been following along in 7.4 and 7.5, and if you've been down with kind of where we've been how we've been building our formulas and then how we've been using them, I think that this section right here is not a very big step to take relative to the previous two sections here. So hopefully you find this to be, I don't know, reasonably straightforward. So we're going to come up with two families of identities today that really collectively form one big old family of stuff, all the ones that will get product sum and sum to product. I'm only going to derive one from each of the families because all of the where they come from is sort of like just kind of doing that same math with different groupings of terms over and over again. So I'll kind of show one of each of them so you get a feel for where they came from. But I think that showing one of them as a representative is sort of, in a sense, good enough. Then, of course, we'll look at some examples with how do we use these formulas to like help us identify values that might be of interest to us. Um, so let's do it. So the first grouping that we're going to look at is the product into sum. So what we want to do is we want to come up with different ways to rewrite these products of trig functions instead as a sum of trig functions. That's going to be our goal for the first section right here. And what I would say to you is, do you recognize terms that look like this? When have you seen trig terms pop up that look like this? And I'm kind of thinking, like in the last couple of weeks of class, I definitely think that you've seen these guys in our sum and our difference formulas. You've seen terms that look like these in those formulas. And I want to re-emphasize to you guys, I really don't expect that you guys are memorizing all of these formulas. I do expect that you guys are able to sort of like generically remember, like, oh yeah, I remember our sum and difference formulas result in a sum of products of sines and cosines, stuff like that. I don't remember what the positives, negatives are, and where the alphas and where the betas went. I got to look that up. But I'm expecting you to kind of have some like vague recognition of general structure here. So what I'm thinking is if I pop back over to our trig sheet over here, do a little zooming in here, that we can look down and see in our sum and difference formulas, I'm seeing a bunch of terms that look like what we're interested in here today, right? For example, over here, I'm suggesting that, for example, maybe we want to look at sine of alpha times sine of beta. Well, I'm seeing some like sine of alpha times sine of beta. Look, there's one right there. There's a sine of alpha times a sine of beta. I'm seeing it right here on our trig sheet, on our sum and difference formula section right here. So what it seems to me is that if I want to come up with an expression for sine of alpha times sine of beta, what I should probably be doing is playing around a little bit with our sum and difference formulas to see if I can, in a sense, extract this term from this guy. Now, what my issue is going to be is that if I want to just get sine of alpha, sine of beta alone, I don't want to be introducing something like cosine of alpha, cosine of beta. So my question is, how could I get rid of that? Well, maybe if we did a little bit of combinations of these things right here, then maybe I can get some groupings to cancel while getting some other groups to join up to arrive at a product of two functions that is only expressed as the sum of some remaining components, right? So I'm going to have to clearly do like a little bit of algebraic rearrangement, but again, I'm doing the same thing we did in the last several videos now, which is saying we really only did really hard work one time to get our very, very, very first formula, which I believe was the cosine difference formula, was the one where we needed like the distance formula for it. And every other formula that we've come up with has just been a rearrangement of stuff that we had previously seen before. And that was really convenient. We're using old parts to build our new parts rather than building anything from scratch. So again, today we want to build expressions for how to rewrite individual chunks like these in the sum and difference formulas as just sums and differences of trig functions here. So it looks like these are the parts I'm going to be able to somehow craftily rearrange to come up with the new ideas, new relationships that I would like to be able to express here. So what I'm suggesting is let's combine some of these old formulas right here, and exactly as I'm showing you over here, it looks like if I looked at my sum formula for cosine right here, or sorry, my difference formula for cosine here, and my sum formula for cosine here, it looks like if we combined these two guys right here, I would see all of my sine terms cancel because I have a negative and a positive, and I would have all of my cosine alpha, cosine beta terms get doubled up right there. Um, Hey, your math student. Yeah, I'm switching up my schedule just slightly today because of a meeting this afternoon. So sorry, I'm changing times on you right here, but we'll still get all these videos posted here by, we'll get the differential equations video made tomorrow and it'll get posted. So I'll be 1 day delayed on the differential equation stuff. Yeah. So I'm thinking to myself, I'm going to do some combination of these two cosine formulas right here to try and get at one of these product terms here to see if we can rewrite it as a sum. So let's go ahead and do that. So I'm noticing here my cosine difference formula for cosine is cosine alpha, cosine beta plus sine alpha, sine beta. So let's go ahead over here and do that. Cosine alpha, cosine beta. I've got a cosine alpha, cosine beta plus sine alpha, sine beta. The other one that I'm interested right now is in the sum formula for cosine. So let's pop back over and look at that. My sum formula for cosine looks like it's the exact same thing, just with a minus sign instead of a plus sign right there. It's the only difference that I'm seeing between the two. This term is the same as this term. The sine terms are the same. The only difference is we're swapping out the plus sign that I just wrote for a minus sign instead. Back over here, let's do exactly that. Cosine alpha, cosine beta, minus sine alpha, sine beta. And the nice thing that I'm seeing here is it looks like I could just do some addition of this entire, I can add these two equations together and notice what happens when I do this addition. On the left side of the equal sign here, I'm going to get cosine of alpha minus beta plus cosine of alpha plus beta. On the right-hand side over here of the equal sign, what I'm seeing is I'm adding these guys up. So it looks like I'm getting two copies now of cosine alpha, cosine beta. And over here, the sine terms, they all canceled. I'm adding together positive sine alpha sine beta to negative sine alpha sine beta. So that's just plus 0 out there on the end. The sine stuff all canceled. And look at what we managed to do. Our goal was to come up with one of these three formulas, and it looks and to rewrite them as a sum of sine and cosine terms, and I did exactly that. I've got cosine alpha times cosine beta, just like we wanted right here, and I've re-expressed it as a sum of trig functions instead of as a product of trig functions right there. All I'm going to do to wrap up this formula is just divide both sides by 2 right here is all I think I need to do, and we are good to go. So it looks like I'm getting here. And by the way, I'm going to flip this thing horizontally right here just because I like to think from left to right. We typically use this formula to take a product and turn it into a sum rather than the other way around. That's what our next set of formulas are going to be. So I'm just going to kind of flip this and divide by 2 and say cosine alpha cosine beta equals 1/2. And I'm going to use brackets here just to follow the book's notation, just to make sure. It's nice to use brackets so that we don't get confusion between parentheses and brackets here. Alpha plus beta, and there we go. So it looks like we've got our first of the three. Oh my goodness, drawing straight lines, hardest thing ever with this digital stylus here. So there's my first formula. It's going to take a product of cosines and re-express it as a sum of cosines. And all we had to do is we literally just added together two of our sum and difference formulas just to set them up so that two of our terms canceled, two of our terms doubled up, and we just had to do a division by 2 and we were done right there. So pretty easy where these guys come from. It's just a combination of two appropriately selected sum and difference formulas right there. And we now have a product into a sum formula right here. So the other two come from doing very, very, very similar steps. And so I'm just kind of writing out the three of them right here. We just did this middle one together. The first one and the third one come from very similar math as we just did up above. You just got to choose different sum and product, or sorry, sum and difference formulas to combine together. You can see the structure of all three of these formulas is the structure of all these are identical. Which terms go where is the particular detail right here. But again, this is where one of those things where it's like, I don't expect you to memorize them, but I expect you all to be able to like, vaguely see just the structure of these things and kind of like recognize that. So when you see terms that look like this in the future, you can say to yourself, I feel like I know something that sort of looks like that. Let me go look up my sum to product or product to sum formulas here and see if I can get some rearranged version of some things here. So here's our three product to sum formulas. All three of where they come from is just rearrangements of our sum and difference formulas right here. So let's go ahead and use these to take a look at an example right here, see where this is going to be practical for us. So suppose that we know cosine of 2 times an angle is going to be 2/3. What I am interested in you determining for me is the product of cosine of 3 times the angle times cosine of just the angle right there. All right. So since I see that the desired value of interest right here is a product of two cosines, I'm thinking to myself, I know ways, because my issue right now is just because I know cosine of 2 theta, it does seem to me, by the way, it seems to me like I could use a half angle formula to get cosine of 1 theta for this guy right here. But I don't have a direct way to get from cosine of 2 theta to cosine of 3 theta. That seems problematic for me. It's not double 2 theta, and it's not half of 2 theta. Um, there are several ways to do this problem, by the way, but I think using this product to sum formula is going to be our quickest route to a solution here. And again, there are many ways I could do this problem for sure without using product to sum formulas, but I think in this case it's our easiest route. So again, my big I want to say red flag verbally here, but this is really more of a green flag that says, hey, I see a product of trig functions. I know I can rewrite them as a sum or difference of some trig functions here. So here's what I'm seeing. It looks like in our setup right here, I think the thing I want to do for myself is name 3 theta to be alpha and 1 theta to be beta so that I can think in terms of the structure of these formulas here. So remember, I think that a thing that a lot of math students, I think that a common theme that I see in people that have like sort of like less math confidence is one of the particular places in which I see sort of like a lack of confidence is people don't want to like name stuff because they're like, I don't know, there's sort of like some like fear of doing something wrong. Give names to quantities, especially when you're trying to apply a formula to a general formula to a particular example. You should say, well, where do I see those components in my particular case in the example? Here, I'm seeing this looks exactly like cosine alpha, cosine of beta. If we name alpha to be the same thing as 3 theta and beta to be the same thing as 1 theta, naming those like that then helps me see exactly how I'm going to rewrite this here in a moment. All right, so it looks like what we're interested in doing is using this middle formula here. So I'm going to say, I'm going to write this one all out here. Cosine, oh, stop doing your crazy highlighting here, word. Relax. Cosine alpha, cosine beta equals 1/2. Just follow my formula here. Cosine of alpha minus beta plus cosine of alpha plus beta. So let's see if this is going to be helpful for us here. We've got cosine of 3 theta, cosine of theta equals 1/2. Now, I'm using 3 theta in the alpha slot. So I'll put a 3 theta in the alpha slot. I'm using 1 theta in the beta slot, so I'll put a 1 theta in the beta slot right there. Very, very similarly right here, we'll get a cosine of, it looks like 3 theta plus theta for this guy. And now, and again, as it's been for this whole entire chapter, I am not 100% confident that what I'm doing is actually going to be useful to me. That's the way that most of this trig rearrangement goes is you got to be okay with just trying some stuff and saying to yourself every step of the way, saying, is this helping me? And right now my answer is I'm not sure, but I can at least clean this up a little bit more and see if this seems like something that's going to be useful to me. So it looks to me like what I'm getting here is 1/2 of cosine of 2 theta plus cosine of 4 theta. And my question to you is, does this seem like a more helpful place to be in than where we started? I think that the answer is yes, because I know exactly what cosine of 2 theta is. That's just straight up 2/3. I get to just directly substitute that in. Cosine of 2 theta is 2/3. I already know my first term. Cosine of 4 theta, I don't directly know. But I know that the angle 4 theta is exactly double the angle of 2 theta. So it seems like I can use my double angle formula to help me out with this guy right here. All right. So I'm going to say to myself, what was my double angle formula? Well, I forgot, but I know that there is one, and that's all I really need to know, right? So let's go ahead and remind ourselves what's up with this. So again, this term, we're done. That's just 2/3. We just need to deal with what's going to be the deal with cosine of 4 theta. But since 4 theta is double 2 theta, and they're both cosines, it seems pretty direct here to use a double angle identity to help us out with this cosine of 4 theta here. So let's remind ourselves of this double angle formula. And I'm looking back over here and I'm saying to myself, what is the thing I'm looking for here? Ooh, I'm remembering now that there's a whole bunch of different let me do a whole bunch of double angle formulas for cosine here. Come on, let me scroll. Here we are. A whole bunch of them, right? We have 3 to choose from for this double angle formula for cosine. So which of the 3 do I want to choose? The first one involves cosine of half of the angle. So if this was instead 4 theta, this would be 2 theta. So I'd get this first term just fine, but I don't know sine squared of 2 theta directly. I could actually get it, but that seems like work I'd have to do. The second formula here seems better though. This formula here seems to only involve another cosine of half of my angle that I'm worried about. The angle I'm worried about is 4 theta. Half that's 2 theta. I can do this middle one. Again, this third one's bringing sines into this, which we haven't been talking about. So I feel like this is going to be my helpful formula right there. Cosine of 2 theta equals 2 cosine squared of theta minus 1. So let's go ahead and bring that guy into our... I'm going to do some little side work over here. So I'm thinking to myself, my little side work, I'll change colors here, is cosine of 2 theta equals 2 cosine squared of theta. And I don't remember, was that plus 1 or minus 1? That was a minus 1 on that formula right there. Minus 1. All right. So here's the thing that I'm really seeing though. Remember that this is just a generic placeholder. This doesn't literally have to be 2 and 1. This has to be some angle is over here and double that angle is over here. So this means to me that I could really think of this as cosine of 4 theta equals 2 cosine squared of 2 theta. Right? This angle here is still double this angle here, so I'm still good with my identity. Remember that this being an identity means that any value that we plug in is legit. I just plugged in theta equals 2 theta. That's all the conversion I made right there. Right? This is really just a variable name change right there. So it seems like I can figure out what cosine of 4 theta is now. This should be 2 times cosine squared of 2 theta. Well, that's just 2/3 squared. Cosine of 2 theta is 2/3. So it looks like we're just squaring 2/3. So I'm going to get 2 times, what's this, 4 over 9 minus 1. And it looks like that's going to be 8/9 minus 1, also known as negative 1/9 right there. I think I can cruise along with exactly the math that I was interested in doing right here, right? So I'm going to kind of bring this value in here and say now we're looking at what? 1/2 times. Here, let me get my I want to finish being appropriate with my work showing right there is cosine of 4 theta. So we were told that cosine of 2 theta is 2/3. So I'm just writing cosine of 2 theta is just 2/3. We just used our double angle formula to figure out what cosine of 4 theta was, because cosine of 4 theta is double cosine of 2 theta. We figured out by using the identity that it was going to be negative 1/9. And hey, we're just evaluating now. We did the trig. Now we just got to do a little bit of fraction math right here, everybody's favorite. I'm seeing here, it looks like I'm doing addition, subtraction of fractions, so I want to get a common denominator. Looks like I can easily get a common denominator of 9 here. So multiplying 2/3 by 3 over 3 gives me 6/9 minus 1/9. So half of 5/9, just doing a little bit of multiplication of fractions here. Looks like that has given me 5/18 is my final answer right here. Kind of odd fraction to be getting out from a product of 2 trig functions right here. But again, Here we were able to use our product to sum formulas to convert some trig expressions. And again, I could have easily used my half angle identity to get a good expression for cosine of theta. I could have done that from cosine of 2 theta, no problem. But this cosine of 3 theta was a little bit awkward because it wasn't double and it wasn't half of any angle that I previously knew information about. But by using our product to sum formulas, I converted my me needing to know about 1 theta and 3 theta to me needing to know about 2 theta and 4 theta. And both of those were relative. One was directly accessible. One was just one identity away from us right there. So this is a good example of when this is kind of practical for us to use our identity to rewrite a kind of hard expression as a little bit easier of an expression right there, one that we can actually evaluate right there. So cool. So there's our first example right there. Our product to sum formula came from two different sum and difference formulas. And then to do this example, we needed to use a double angle formula. And again, a different strategy for this problem would have been to use a half angle formula for this one. So a lot of these identities, I hope that you're seeing this now, are going to continually be interrelated with one another. And you need to kind of constantly be saying to yourself like, out of all, we were coming up with like 20 identities in these three sections right here. And you need to be able to say to yourself, how would one of these identities help me rewrite this expression into something that's a little bit easier for me to manage? And that's exactly what we were able to do right here. So let's look at going the other direction now, our sum to product formulas. These formulas are going to go the other direction, right? What I want to do now is I want to convert sums and differences of angles into a product of two angles. And we're going to motivate why would we care to do that in a minute here. I think this one here is a little less obvious in a sense right here. Hey there, Professor Melko, how's it going? I've spent my morning watching chemistry lectures with Professor Melko on Twitch here. He's here to get his trig on over here. We'll be doing our programming and our differential equations to go with your chemistry things here in tomorrow's videos. So our sum to product formulas right here. These formulas go the other direction, right? We're going to start with a sum and convert to a product. It's a little bit less obvious how we're going to do some math to get from one of these to the other right here. The book really bails on doing the derivation for this one, which kind of bothers me. They're just like, look at this statement that's true. And it's obviously a true statement when you look at it, but they don't say like how they thought of how to get those terms. So I'm going to kind of show the motivation for this derivation as well right here. And ultimately, as I'm saying here, it just requires that we're a little bit crafty with some fractions. It's nothing too crazy. So let me show you where this comes from right here. One thing I do want to point out real quick is that you should notice with these formulas that we're building today, these only relate sines and cosines. There just generally aren't similar collections of these things tied to our other trig functions that are used out there. This family of identities is kind of fortunately for us, only tied to sines and cosines, which is where our comfort zone is. Even more particularly for this one right here, you should notice that. Dang it, what are you doing here, pen? You should notice that not only are there only sines and cosines, but in these formulas here, we're never even mixing and matching. These are only for adding together two sines, adding together two cosines, subtracting two sines, subtracting two cosines. We're never even going to get a formula that's like, what's up with sine of alpha plus cosine of beta? Not really a good general formula that we're going to be able to find for that guy here. So let's go ahead and just like we did before, let's find one of these. The other four formula or the other three formulas out of the four are going to follow from a very, very similar place. And the question I would ask you is, where have we seen a sum of two different sine terms, for example? And the answer is hopefully quite obviously about 10 minutes ago, right? We just did this, right? We've got a sum of two sines sitting right here. There's a sum of two sines right there. So maybe I can just take my product to sum formulas and try and turn them inside out, right? Now here's the difference. When I wrote this formula up above, like why did I want to like flip this thing left and right like I did? It's because I kind of like to have sort of like my where you start on the left and where we go on the right, just because we read English from left to right. But you should notice the special part about this formula, which is that the simple angles were on the left. Our slightly more complicated angles were on the right. We're going to kind of want to flip that inside out now. What I want is an identity that almost looks exactly like this. But my issue is I would really like these angles to be the simple parts because I want to take, for example, cosine of 20 plus cosine of 50. I want those to be the angles that I just straight up know. What I'm therefore expecting is if these are the simple angles, then I'm expecting to get a term that kind of looks like this one over here, but I'm expecting to have a slightly more complicated expression where there's currently alpha and beta sitting right there, all right? So I'm expecting, like I said, I kind of picture this as like kind of turning this formula inside out right here. So let's go ahead and start with the thing that we saw a minute ago. I'm going to start with my product to sum formula that produced two signs so that I can get two signs, an expression for a sum of two signs right there. So which one was that? I want to basically just start. In fact, I'm just going to copy and paste this guy down here. That's what I'm going to do. This guy has our sum of two signs in there. So let's see if we can invert this guy, flip it inside out. So here's kind of where I'm starting from with this. Now, here's sort of my thought process that goes along with this guy. Kind of what I'm thinking to myself, as I said a moment ago, is that I'd really like for these. Oh man, get out of here, Microsoft Word. I'm writing right now. You're fine with this. Relax. There we go. Okay. I don't want these to be my complicated terms. I want these to be my simpler terms right here. So there's two things that I want to kind of do first right here. One, I don't want this 1/2 anymore because I'm sort of trying to solve for this expression right here and just kind of clean it up. So one thing I'm going to do is I'm going to multiply by 2 on both sides. But as I've said several times now, these are the terms, these are the angles that I don't want to be some complicated thing like an alpha plus beta. I want them to be a simple thing, like it would be nice if it was just alpha and just beta in there. So I'm going to name them something. I'm just going to name them x and y so that there's something, a single term. And what I'm going to want to know is, how are we going to be able to write this alpha and beta in terms of x and y, all right? So here's my move right here, is I'm going to say, let's define sine of, or excuse me, sorry, that's not the sine of anything. I just want to define just a renaming of some angles. X to be alpha plus beta, and y, oh man, I want to get this in blue so I'm nice and color organized here. X equals alpha plus beta, y equals alpha minus beta, right there. And the point is I want this to be the simple side of the equation. I want this to be the whatever it's going to be, a side of the equation over there, right? So it looks to me like I'm getting 2 sine alpha cosine beta equals sine of x plus sine of y, right? So what I've done is I've just created some new variables that make the right-hand side simple. And so now my question to you is, what are alpha and beta in terms of sine and cosine? Or sorry, in terms of x and y, right? So now it's sort of like I want to kind of start with the values x and y, and I want to produce something that's going to look like this over here. So I want to know, can I replace alpha and beta with some expression in terms of x and y? If I have that, I'm done, because then I'm taking a sum of two simple sine statements and turning it into a product of sines and cosines with whatever I need in the parts right there, right? So here's what I'm going to do is I'm going to do a little bit more addition of equations like we actually already did a little bit of here today. I'm going to do x equals alpha plus beta as one equation, y equals alpha minus beta as my second equation. I'm going to add them up. And what I'm seeing here is I get x plus y on the left-hand side of the equal sign. I'm seeing that I'm getting 2 alpha by doing addition. And I'm seeing that I get a 0 from the beta component right there. And so it seems to me like I've found here, if I just divide both sides by 2, that I'm getting x plus y over 2. And if I go ahead and I plug this back in then to either of these equations, I suppose, then I could go ahead and say something like x equals alpha plus beta. Well, alpha I've found to be x plus y over 2. Stop doing that crazy thing up there, Word. Having a little seizure up there. This is plus beta, right? That was alpha right there. I think I can just write this guy. I want to get this in terms of, right, I'm trying to solve for what beta is going to be. So I'm going to go ahead and subtract this over to the other side. And I might think to myself something like 2x over 2. That's my original x term right there. Minus x plus y over 2 should be equal to beta. Man, I wish I could have got this all on one screen right here. Almost. And so it looks like I'm doing 2x minus 1x gives me just a single x right there. But notice this negative is still also attached to the y. So this is going to be giving me, man, I wish I could have lined that up a little bit better. X minus y over 2 equals beta. And the point of what we've done now is this. What we ended up finding here was a way to rewrite alpha and beta in terms of that x and y that I'd created. So now this finally allows me to say, and now I'm going to kind of rewrite my last line here, which was 2 sine alpha cos beta equals sine of x plus sine of y. And now I have a way to write alpha and beta in terms of x and y. And so again, I'm just going to flip this formula left to right since I like to see sort of my input side on the left and my output side on the right. As sine of x plus sine of y equals what? 2 times sine of alpha, where alpha is x plus y over 2, times cosine of beta, and we found that beta was x minus y over 2. So when I say that I flipped this formula inside out relative to the previous family of formulas, I really mean, one side of the equation had complicated angles and one had simply defined angles. Here, like x and y, above, like alpha and beta, right? So here I took the complicated side, alpha plus beta, alpha minus beta, and I made it the simple side, x and y. I then needed to figure out how to make what was currently the simple side, alpha and beta over here, and turn this one into the complicated side. It's really not that complicated. It's x plus y over 2, x minus y over 2, right? But we've come up with our formula here by kind of like flipping this inside out, naming a group of terms. Naming is key right here. If I didn't do this, I have no way to kind of identify what this formula is actually going to be right here. Resolved these two equations that are currently solved for x and y. I solved them instead for alpha and beta so that I could re-express this in terms of x and y instead of alpha and beta right here, and we got our formula. So these are our 4 formulas. Notice it is back in terms of the alphas and the betas. So this is like sine of alpha plus sine of beta equals 2 sine alpha plus beta over 2 cosine alpha minus beta over 2, stuff like that. But you can see that, again, all 4 of these formulas have identical structure. Their components have changed a little bit. Positives, negatives have changed a little bit. Dropping that negative is a hugely popular thing for students to do out there because it's the only formula that has a negative sitting out front right there. But again, the structure of these 4 are identical. So I expect you to recognize these structures. If you see things that look like this, I expect you to say, ooh, I think that's one of my product to sum or sum to product formulas. Let me go look it up real quick, right? So general recognition is expected. Memorization is certainly not. These especially, I mean, man, if there's one grouping to not memorize, it's probably this grouping right here, but you should recognize this format of these guys right here. So let's go ahead and do an example. And what I want to say, since this is our last family of identities, by the way, let me pop over to the identity sheet over here. You should feel good that by right now, this was all chapter 6 up top. This was also chapter 6 right here, the fundamental identities. This was also chapter 6, even odd identities. Here was section 7.4, all of our sum and difference formulas. There was 6 of them. Here was 7.5, our half angle and double angle formulas. There's another 8 of them, so that's 14 formulas. Plus, that's actually 3 more formulas we came up with for the squared formulas that were kind of intermediary here. So what are we at right there? It's 17 formulas. Plus today now in 7.6, we just got 3 more and 4 more. We're at 24 formulas that we've come up with in the last 3 sections. That's so many, but you should feel good that we're like done, right? I can fit it all onto one page right here. Here's like all these formulas that we got in chapter 6 and 7. The last thing we got to cover is just a couple of these guys out here in chapter 8, and that's it for this whole dang formula page we've almost covered. So this is my proof that we're done with formulas, is that there's nothing else on your formula page back here. But again, you should kind of feel like good that we've kind of like completed, like we know where all these come from now, and we've seen a reason to believe them, and we've seen examples associated with them, sort of. I feel like what a reasonable math student should be saying right now is like, holy cow, dude, what are we going to do? Just come up with infinite formulas that relate sines and cosines? Like, technically I could. If you look in your trig textbook at the homework sections for these proof verify or these identity verifications, it's like I can literally come up with infinite statements that relate some trig expressions to some other trig expressions. What makes these ones useful to me at all? Why would I ever care to do this? What I would like to argue to you right now is that when it comes to equation solving, which is sort of what the end goal of this whole chapter is, we're about to get to 7.7 and 7.8, It's 2 sections on solving trig equations. I don't want to make you scared and say it's hard, but it's kind of hard. And the point is, we're going to need to reformulate our trig expressions into being something solvable. And not every grouping of trig equations or trig expressions equal to other trig expressions I can solve. Most of them, honestly, I probably can't. So in lots of cases, we want to take expressions that are difficult to manage and turn them into something that's nicer to manage. But when I say difficult and nicer, in what context do I mean? Well, in equation solving, it turns out that it's often, very often, much nicer to deal with products of expressions than it is to deal with sums or differences of expressions when we're in a solving scenario. So this guy right here is actually very practical for our equation solving stuff that we've got coming up right here. And the reason why is because of the thing that's called the zero product property. So I'd like to remind you a smidge of algebra right here that we're going to take advantage of in our example that we're about to do, right? So I want to remind you guys that this equation right here, you absolutely cannot directly solve for x in this formula. You cannot just do addition and subtraction and maybe a square root and just get there. You've got to do some kind of specialty quadratic stuff to actually make this guy happen, right? And again, the reason that you can't directly do this is because I can't combine like terms and just get down to a single instance of x. What I have here is 2 different x's that I can't join together, and therefore I have no way of directly getting to like an x equals. We got to do something special in this case right here. The typical, and in fact, there are 2 different algebra routes to this one right here, both factoring and completing the square will get us there. But in this guy, I want to show the factoring route. That's really nice. Well, we can see if we do a little bit of factoring of a quadratic right here is that 8 has product pairs of 1 and 8 and 2 and 4. And I'm noticing that 2 and 4 is both a product that gets us to 8 as well as a sum that gets us to 6, which shows me that I can factor this quadratic as x plus 2 and x plus 4 equal to 0. Now, what I just said a second ago to you is that the reason that you cannot straight up solve this thing is because there's more than one instance of x that you can't join together. My goal is to get to an equation where there is just one instance of x. Then I can just unbury it from wherever it is. And notice here, I don't have just one instance of x. I still have 2 instances of x. But what we want to really remember here is the zero product property is going to say to us this. The special thing that's happening here is this is not just a number times a number. It's very important that it's equal to especially 0. No other number is going to do it for us over here. It's got to be 0. The zero product property is going to tell us that a times b equals 0 means either a or b has to be 0. Right? It's got to be the case. If you ever multiplied 2 numbers and got 0, one of those numbers was 0. There's no other way around it right there. And that's exactly what's happening here. I'm multiplying 2 terms and I'm getting 0. It's a guarantee that one of these 2 terms has to be 0 to make this equation true. And so I can individually set x plus 2 to be equal to 0. Either this term is equal to 0 or x plus 4 is equal to 0. And I can very easily solve these now to get the 2 solutions associated with this quadratic equation. And again, obviously no trig right now on the page whatsoever, but the point is products, especially when they're equal to 0, very, very nice for solving equations, whereas sums, when they're equal to 0, often not very helpful in solving equations right here. So we really like factored form, and you should notice this is exactly what these formulas are doing. They're taking a sum or difference that we can't solve even if it was equal to 0, and we are converting it into a product. Now, if this was equal to 0, we could individually set each of those factors equal to 0 and solve each of the individual components like we did right here. Right? So these don't seem useful to me until we think of them in the light of solving equations, and then it seems to me very practical to rewrite sums and differences as products. It's exactly the same theme as how we solve our quadratic equations right there. Oh, I'm excited about the zero product property hype in chat right there. That's good. That's good. So let's hit this guy with an example. Now, this example is going to be, I'm going to just say, this example is going to be kind of hard because this is, in a sense, me like getting ahead of myself, but I'm only getting ahead of myself by like literally 25 minutes of course video right here because our very next video is solving trig equations. So why don't we just do that as our wrap up to our sum to product to sum formulas today is solve an equation using this property right here. So our goal is going to be to solve this equation for theta. I want to know what angle theta makes that a true statement right there. Now, what I'm going to want this to do, and we're going to talk about this more at length in our 7.7 and 7.8 videos, is I'm going to want a general solution, because what you guys kind of know about your trig stuff, even though we haven't done equation solving yet, is if I said to you something like, what angle gives me a sine of theta being 1/2, well, there's an infinite number of them because sine just keeps on repeating. So we could get, what would we be getting? 30 degrees, but then add 360 to that, get 390 degrees. Add 360 to that to get 760 degrees, right? And you could just keep adding 360 and getting another solution, getting another solution, getting another solution. There's an infinite number of solutions to pretty much all of our trig equations out here. So I want a general set of solutions, and then maybe we can identify just the solutions that fall into this interval right here from 0 to pi, right? So let's see if we can do this here. And again, I'm going to say this is not obvious. I'm going to for sure have to help you along with this one right here, but I think we can do this, guy. So what I'm seeing here is I don't know what to do with these terms being on both sides of the equal sign right here. That's kind of making this difficult for me to sort of conceive what we're going to be doing right here. So my first thought with this guy is maybe let's try and I want to get these guys to hang out. They seem like they should be buddies. Let's make these guys be a little bit more friends than they currently are. Sine of 5 theta, maybe if I subtract over the sine of 3 theta to this side, we can see something nicer. Now, here's the thing that I'm seeing. It looks like these two guys want to play together. And every time I see equal to 0 when I'm solving equations, I'm thinking to myself, oh baby, if I can make that left-hand side be a product of two functions, then I've got the 0 product property is just hitting me in the face right here. Equal to 0 is your friend if you can rewrite this expression as a product. And right now it's a sum or difference. So I think we're in really good shape to do that. So it looks to me like we have a difference of two sines. So let's go ahead and see what our formula looks like for this guy. Our difference of two sines formula is right here. 2 times sine of the difference times cosine of the sum. 2 times sine of the difference. I guess I should write it over here to the side. Sine of alpha minus sine of beta is 2 times sine of the difference, alpha minus beta over 2, times cosine of the sum, alpha plus beta over 2. Am I falling off the edge over here? Almost. All right. So it looks like that's the formula that I want to use in relation to this. So it looks like I'm thinking of 5 theta being alpha and 3 theta being beta. So if I were to use our identity over here now, it looks like I'm going to be able to rewrite this as 2 times the sine of alpha minus beta is 5 theta minus 3 theta over 2 times the cosine of alpha plus beta over 2. Alpha is 5 theta, beta is 3 theta. So we're going to get a 5 theta plus 3 theta over 2 equals 0. Let's go ahead and simplify these to see what these kind of panned out to right here. It looks like I've got a sine of 5 theta minus 3 theta is 2 theta over 2. Well, it looks like that's just going to be the sine of theta. That worked out pretty nice. Over here, I'm seeing the cosine of 5 plus 3 is 8 theta over 2. That looks like that's just going to be cosine of 4 theta equals 0. And so notice that what we've done now is we had two things being equal to each other, subtracted one over to make it a sum or difference, used the sum to product formula, or here the difference to product formula, to rewrite this as a product. Now I get to use the 0 product property, right? Now what this is saying to me is, listen, since you're multiplying together, really, and actually I'd say there's 3 different things that we're multiplying up here, right? This is like A times B times C equals 0. Well, in that case, it either needs to be the case that A is equal to 0. That never happens, so that didn't get me any solutions. Or it needs to be the case that sine of theta is equal to 0. Ooh, that does happen. I'm going to get some solutions out of that guy. Or it needs to be the case that cosine of 4 theta is equal to 0. Ooh, that one's a little bit weirder right there. We're going to have to be a little bit more careful on that guy. So So one thing right here is to say that 2 doesn't really matter. I could have just divided both sides of this equation by 2 also, and 0 divided by 2 would have been 0. It's not contributing anything to it right here, right? 2 is never equal to 0, so it's never contributing solutions according to the zero product property. So now I'm going to ask you, when is sine of theta equal to 0? And I'm just picturing my unit circle, right? We're definitely going to do some unit circle consideration here. So thinking back to my unit circle, when is sine of theta equal to 0? I know that sine is measuring my y value on the unit circle, and I want to get out a y value of 0. So what I'm thinking to myself is that these are two good locations, at 0 and at pi. But I know that there's technically an infinite number of answers, right? I know that sine of 496 pi is also 0 because it's a whole number multiple of pi. 0, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. All those things have a heights of 0 on the unit circle, and all the negatives, right? Negative pi, negative 2 pi, negative 3 pi. We just rotate in the other direction, right? So it seems like my answer to this guy is, in general, theta equals just pi k. It's all of our constant or all of our positive sorry, wow, I just said those both wrong. It's all of our integer multiples of pi. That if we take the sine of any of those values, we're going to get 0 out right there for our solution, right? I'm going to go ahead now and do the similar thing over here. But the difference is, and in fact, I should write one extra line in here real quick, by the way. This is like me doing theta equals sine inverse of 0, but I know that I'm technically potentially getting an infinite number of answers, not just what I'm going to get from this guy. This guy will tell us 0, but it could have been any of those other constant multiples right there, right? So 0 plus pi k right there, or I'll just say theta equals pi k. So a little bit, me getting a little long-winded right there, but that's okay. The point is, I want to kind of think the same thoughts over here. When is cosine of some angle going to give me 0? Well, I know that cosine is 0 at the bottom and the top. This is when is my x component equal to 0 on the unit circle. That looks like it's happening here at pi halves and then 3 pi halves. But what's the next one after that? 5 pi halves, 7 pi halves, 9 pi halves. So it seems like this is the place where our angle, and notice here, our angle isn't just theta, it's 4 theta. And again, I'm doing the thing I kind of, well, whatever, that's okay. Should be equal to pi halves plus pi k. Those are all the angles that would result in a cosine of 0 right there. First is pi halves, then it's 3 pi halves, but I could just keep going forever and keep on doing an additional pi rotation to get to the next place that cosine of that angle is going to be 0. So notice here, we have one last little baby algebra step to do. If my true goal here is to find what theta is going to be, we've solved for 4 theta from this equation. I need to divide everything by 4 to get what theta is going to be for this contribution here. So it seems like theta is going to be, dividing this right-hand side by 4, it seems like we're going to get pi eighths plus pi fourths k, right? So this to me looks like my general solution. This looks like, in terms of k, my general solution is all values of theta such that theta equals pi k or theta equals pi eighths plus pi fourths k, where k is an integer. What I want to still find out, though, so that's my general structure of what an answer would look like. I want to know specifically in the interval from 0 to pi. That was our other question here. So that was our general solution. These are the infinitely many things that we just described in terms of k. Now what I want to know is, out of all those infinite solutions, which are the ones that fall in our first half of a unit circle from 0 to pi right here. So let me say here. Let me do it, Microsoft Word. Be my friend. There we go. There we go. And so I'll switch to blue here. Particular solution. Which of these, when I say these, I mean these guys, fall in the interval 0 less than or equal to theta less than or equal to pi? That's the remaining question here. So all I'm really doing right now is just saying, well, what values of k should I use? Let's just pick some k's, right? So I might even go so far as to like make a table right here and maybe call this theta 1 and theta 2 for myself. This is just my way to stay organized. Certainly don't need to make a table, but I don't know, be organized. Why wouldn't you be? So the first thing that I'm seeing here is it seems like where do I even want to start k at? And notice, by the way, I could totally ask you a question where I'd say, in the interval from negative 3 pi to negative 2 pi, where are the particular solutions? Well, in that case, you might want to think about some negative k's. Here I'm thinking that 0 is the smallest thing I'm interested in, so k being 0 seems like a pretty good place for me to start with this guy. But again, you might want to play around with some like backwards k's and some forwards k's right here, you know? So if k is 0, then what does theta 1 give us? It gives me 0. What does theta 2 give me? It gives me pi eighths plus 0, so just pi eighths. Both of those fall into my desired interval, so it looks like both those are good answers. What if k is 1? Well, if k is 1, then theta 1 is going to give me pi. That seems like that is at the edge of my interval. That's at the final ending of the interval right there. Over here, if I make k be 1, I'm going to get pi eighths plus pi fourths. We'll do all my side math over here. This should be pi eighths plus 2 pi eighths, right? That's pi fourths. That's giving me 3 pi eighths. So that seems to be what I'll be getting right there. All right. So what I'm kind of seeing here is if I go off on a k being 2, I know that this is not going to be providing me one of the solutions that I'm looking for, right? That is outside of my bounds of interest right here. So I'll put a little red X next to that guy. But I am seeing that this guy should just be getting an additional pi fourths beyond 3 pi eighths. So that's going to be giving us 5 pi eighths. 5 pi eighths is still less than pi, so that's still within our good interval right there. So it does look like I should kind of keep on going a little bit longer right here. Again, if I do 3, it's going to give me 3 pi. That's not quite in my interval right here, so I'm again going to put a little red X next to that guy. But again, I can go another 2 pi eighths or pi fourths further beyond this one. I'm going to get a 7 pi eighths. And if I did that one more time, I'd be getting here 4 pi, which again, not in our interval of interest. I'm just kind of trying to be like really showing all my work here. Here we'd get to 9 pi eighths, and you should notice 9 pi eighths is beyond the edge of our interval of interest. So that one no longer qualifies as well, just for our particular interval that I gave right here. So it looks like 0, pi, pi eighths, 3 pi eighths, 5 pi eighths, and 7 pi eighths are the 6 particular solutions that landed in the interval from 0 to pi. So our particular solutions so sine of 3 theta equals sine of 5 theta over 0 less than or equal to theta less than or equal to pi are theta equals, and I'll put them in a list. You should use curly braces when you're indicating a list of values in math here. And I'll list them in the order that they kind of go. So 0 is first, then it looks like all the fraction ones come next, and then pi is the biggest. So as my last thing here for the day, I want to say to you, holy cow, do you really believe me that that's going to be right here? I don't think that you should. I don't know. Would you trust this face right here? Let's go ask something that's more reliable than ourselves to verify this for us here. So what I'm going to go do is ask the true source of all knowledge here. And I'm going to look at sine of 3x, and I'm going to look at sine of 5x, right? And when I do this, what I'm looking for is our question is, when are sine of 3x and sine of 5x the same? So this is not a very generally helpful graph for me to look at right here. I'm going to go ahead and modify my graph settings. I know that I'm interested in these x values, right? The x is like theta here, and our theta was going from 0 to pi. So just to give myself a better viewing window, I'm going to go from like -1 to pi plus 1. If you go just from 0 to pi, then there's values that are of interest to us that are like the literal edges of the graph. I'm trying to like give ourselves a little buffer space out there. I also am pretty confident that our y values don't need to be that crazy, but I'm not too worried about that guy right there. And often I do like to give myself, I know that I'm kind of thinking in terms of pi eighths here, so maybe that's a useful thing to see. So what I'm going to see right here is my question is, when are these graphs the same? And here's where I'm seeing. Looks like they intersected at x equals 0, at x equals pi eighths, at x equals 3 pi eighths, at x equals 5 pi eighths, 7 pi eighths, and pi right there. So it looks like their intersection locations between 0 to pi had these x values that were exactly the solutions that we just came up with. There's all 6 of them that I'm seeing right there. So recognize that, by the way, I don't even think Desmos supported identifying these in terms of pi until like a year or two ago. So aside from the fact that you guys are like the first generation of students to ever even have Desmos, Desmos is even giving you exact answers in terms of fractions of pi instead of just obnoxious decimals. Like if you typed in 3 pi, like, it used to be a few short years ago that Desmos would have been telling you just numbers like this. 1.178 is all you would have seen at that intersection right there. I have a hard time believing any of you would have been like, oh, that's 3 pi eighths right there, right? That wasn't going to be happening. So feel happy about this. Now, of course, I do want to point out to you, of course, when you guys go to take your midterm, which appears to be, gosh, it seems like my wife's just never going to have this baby, so it's apparently still going to be a while. I think it's going to be after spring break at this point. Certainly, this is something that you should be using to check your answers with these guys. But of course, I am highly uninterested in you saying I checked Desmos and these are the answers. I am very, very, very interested in seeing your guys' ability to actually solve the equation and prove to me based on your own knowledge what the solution is right here. So again, this is a kind of harder example, but this is what we're covering in our next 2 sections right here. So what we're going to talk about in the next 2 sections is a lot more about this general solution in terms of k versus particular solutions over a specified interval. This idea that we want to just sort of plug in k values until we think we've seen all the possible values that could come out of our general solution to belong in our particular solution, stating our general solution sets using our curly braces with our set notation there mathematically, and recognizing that when we go to solve trig equations, in general, they very often have infinite solutions. Oh, when we specify an interval over which we're looking for particular solutions, not uncommon at all for us to see that we're going to get like 6 answers, 12 answers, stuff like that over some defined interval of interest right here. So I do think that this is something that's relatively typical of what you would expect in the coming up sections right here. But I will say I would consider this to be in the medium difficulty of problems right here. This is not like we're going to see stuff easier than this when we talk 7-7 in our next video. But once we get to the end of 7-8, we're going to see some stuff that's even a little bit more complicated than this guy right here. So I would say if there's like 3 tiers of difficulty of our trig equation solving, I would put this problem at about our middle tier right here. So I expect this to be a challenging one, even once we do cover 7-7 and 7-8 for you guys out here. But I felt like it was a good idea for me to sort of preface this as we're wrapping up all of our formula finding adventure right here from these last 3 sections. So I'm proud of myself. I'm under an hour right here. Good job, Tony. High five. Yeah, man. So that's going to wrap it up for our sum to product and product to sum formulas. You now have 7 new formulas available to you to rewrite some of your trig expressions out there. If you have a product and you don't want it, you can write it as a sum. If you have a sum and you don't want it, you can write it as a product. These are both going to be helpful for us in our solving of trig equations in the next 2 sections. And man, I got to say, I'm positive that not everybody watches every one of my videos. 7-7 and 7-8 are harder sections, and I definitely I anticipate complete viewership for these because there's just a little bit more challenging content coming up with these guys. But then we're done with chapter 7 right here once we get 7-7 and 7-8, and that's going to happen nicely. That we're going to get through those, or at least through 7-7 next week. And then we got spring break right after that coming up right here. So, and I guess that'll be my kind of like wrap up statement here is since I'm making these videos now for the week before spring break, it appears to me like we are going to make it through spring break or through to up until spring break. Then we're going to have spring break. That means to me that my wife's having a baby in the next 10 days sometimes, which means it seems very highly likely that our midterm exam is going to fall the week after spring break. Will be the week that I'm not going to create new content. I'm going to sit at home with a baby. You guys will be taking your midterm, it seems to me, the week after spring break. So plan on that right there. I will see you guys in our next video for section 7.7. Have a good one, everybody. Good to see you, Professor Melko.